some fun shaded region problems. So we're going to go through these. So you should have printed out this handout, some fun shaded regions, as well as one entitled Shaded Region Problems. And we can go ahead and start with the Some Fun Shaded Regions handout first. We're going to skip over ones that have after 16-5 on them. That's going to get into something we haven't kind of talked about yet. But we'll do that in the 16.5 lesson. So we're going to do some of these. And what I would suggest that you try and do, because normally we would kind of do these in class for a few of them, and then I would have you do them for homework. In fact, I think that's how I have it listed in Schoology. I'm actually going to go ahead and go over all of them. But what I really encourage you to do is try it yourself. Some of them are fairly easy. Some are very difficult. And then actually, watch me go through it and hopefully verify your correct answer. Remember, there's more than one way of doing these. So that's, totally fine too. There's only one correct answer, of course. Okay, so notice the instructions. Find the area of each shaded region. Assume polygons are all regular. Okay, so you can assume that any polygon you see is a regular polygon. Okay, so on number one here, go for it. Give it a shot. Pause your video and then we'll come back. Okay, so the way I set this up was realizing that it's three triangles. That is the shaded region. So what I needed to do was figure out what the area is of each of those, and then obviously just multiply it by 3. So in blowing up kind of one of these triangles, I knew that this was side length 6, right? So that's here, and then obviously this would, because it's a regular polygon. In this case, it's a hexagon. I know that the angle here would be 120. How do I know that? Oh, come on, you know how to do that. Anyway, so obviously when I drop an altitude, right, it's an isosceles triangle, I'm going to have 60 degrees, 60 degrees, a right angle, so it's a 30, 60, 90 triangle. So if I know that the hypotenuse is 6, the side opposite the 30 is 3, and the side opposite the 60 is 3 root 3. Well, that pretty much gives me everything that I need because I know that 6 root 3 would be this entire side length here. So this is our base, our height, and we would multiply that times a half and then multiply it by 3. So that would be 3 times 1/2 times 6 root 3. Again, the base and the height is 3. So 27 root 3. Okay, good. Hopefully you got that one. Try number 2. Okay, so we have a square and an equilateral triangle. The side of each is 6. So what's our game plan going to be? Again, always list this out. Notice here I did the 3 triangles. Here, what is it going to be? I did the area of the square minus the area of the equilateral triangle. So that would be s squared minus, remember, s squared root 3 over 4 for the area of an equilateral triangle. All we have to do is plug in 6. So 36 and then 36 root 3 over 4. We can reduce that and we end up getting 36 minus 9 root 3. Again, make sure you don't have a negative answer here. Right? That would make no sense for the area to be negative. And obviously we know 9 times root 3 is less than what 36 is. Okay, we're going to skip number 3 here. We're going to go to number 4. Notice what we have here. We have a semicircle and an equilateral triangle. So give it a shot. So plan is going to be the area of the triangle plus half of a circle. The area of half the circle. So formulas for that, s squared root 3 over 4, and then obviously 1/2 of pi r squared. We need to figure out what s is. Well, we know s is 12, right? So that's easy to plug in. And if that's 12 across, then the radius is half of that, because this is basically a diameter if we had had a full circle. So it's 6. So all we have to do is plug in there. So 12 squared, 144. We can reduce that. And we're going to plug in 6. 6 squared is 36. And end up getting 36 root 3 plus 18 pi. Okay, moving along to number 5. Oh boy, look at this one. Give it a ring. You can do this. You can do it. Isn't it just kind of half of an annulus? So, yeah, the area of half of annulus. So that would mean we need to figure out the area of the full enchilada minus the area of this circle, and then take half of that. So what would be the setup for that? 1/2 of pi r squared minus pi r squared. So what's r, capital R? Well, isn't that 5 plus 2, which is 7? And r is 5. So 7 squared is 49. 5 squared is 25. And so we end up taking half of the difference there, which is, difference is 24 pi. So half of that is 12 pi. Okay, give number 6 a shot. Here's a hint. Draw in the diagonal of the square. Okay, so yeah, it's going to be the area of a quarter circle minus the area of the square. So formulas for that would be obviously 1/4 of pi r squared minus s squared, right? And s squared in this case is what? Well, if I can draw in a diagonal here, and I know the radius is 6 here, isn't this also a radius? So if this is 6, I'm creating what? A 45, 45, 90 triangle. Let me draw this in. So if I have this, and I know that this is 6, obviously I've got a 90-degree angle here. I know these are 45, 45, right? Because I have an isosceles triangle right here. What is going to be the length of the sides opposite the 45s? Yeah, it's going to be 6 divided by root 2, which is 6 root 2 over 2, which becomes 3 root 2. So we're going to plug in. S squared is 3 root 2, right? And we're plugging in radius of 6. We're going to do the math on that. A quarter of 36 pi is 9 pi. And 3 root 2 quantity squared becomes 9 times 2, which is 18. So we end up getting 9 pi minus 18. Obviously, 9 times pi is more than 27, so we end up getting a positive value for the area. Yay. All right. Take a look at number 7. I'm going to change the view on this so that we can see it a little better. Okay, so go ahead and give it a shot. All right, so my game plan was the area of the equilateral triangle minus the area of the 3 circles. Okay. And I'm going to cover that and then cover that. Okay, so formula would be s squared root 3 over 4 minus 3 times pi r squared. 3 times the area of the circles. All right, so obviously I need to get s squared and I need to get r. What are we given? Well, we're given that that is 3, right? And I know that if that's 3, then that's also 3. And I know that that forms a 30, 60, 90 triangle. Again, remember it's an equilateral triangle here. So this becomes, instead of being 60 degrees all the way, bisected, it becomes 30. I know I have a radius to a tangent, so that's a right angle, so it's a 30, 60, 90 triangle. So the side opposite the 30 is 3. The side opposite the 60 is 3 root 3. Okay, so I have 3 root 3 here, and you can see how we basically would have the same triangle over here. So I know this is 3 root 3 also. So how do I get that this is 6? Which means this would be 6. Yeah, it's a radius and then another radius, right? So that's 6, meaning that is 6. We have a rectangle there. So what is our side of the huge equilateral triangle? It's 3 root 3 plus 6 plus 3 root 3, which becomes 6 plus 6 root 3. Okay, so we can plug in that there. And then the radius we know is 3. So 3 squared is 9, so I have 9 pi, and then we have to multiply that times 3. Over here, we're going to square this binomial. So that first term squared is 36. Double the product of the two terms. The product of the two terms is 6 times 6 root 3, which is 36 root 3. Doubled is 72 root 3. 6 root 3 squared is 36 times 3, or 108. That's still all over 4. And then minus, obviously, we can simplify this to 27 pi. Okay, so when we do that, I can go ahead and combine like terms. And I have, remember, I still have that root 3 there. So if I went ahead and distributed, I get 144 root 3. 72 root 3 times root 3 becomes 72 times 3, which is 216. I can reduce all of these because 4 goes into all three parts of them, right? And if I do that, I end up getting 36 root 3 because 4 goes into 144 36 times, it goes into 216 54 times, and then I have minus 27 pi here. Okay, good. Okay, try number 8. All right, so the way I set it up was it's the area of the big circle plus the area it's the area of the small circle plus this annulus plus this annulus. Okay, and I know the center of the both side has a radius of 2 and each band has a width of 2. Okay, so in other words, this distance is 2, this distance is 4, this distance is 6, this distance is 8, this distance is 10. So how would I set that up? Well, it would be, formula would be, I guess I just went straight to it on this one. So pi r squared, obviously, for the circles, and the radius is 2, so that becomes pi 2 squared, which is 4 pi. And then the annulus would be, the inner annulus would be this circle minus this circle. So the area of this circle here, the radius is 6, so it would be 6 squared, which is 36 pi. The radius of this circle is 4. 4 squared is 16, so this smaller annulus is 36 pi minus 16 pi. And then the bigger annulus, the shaded region, would be this circle's area, which is a radius of 10. So 10 squared is 100 pi minus 8 squared, which is 64 pi. So what does that simplify to? That sort of simplifies to 20 pi. That simplifies to 36 pi. Put them all together, and we get 60 pi. Okay, moving along to the other sheet, the one entitled Shaded Regions. I'm going to go ahead and increase the size back up on this. Okay, so we're going to skip number 1. Let's go to number 2. And again, find the area of the shaded region. If it looks like a regular polygon, it is. All right, so go ahead and try number 2. So my game plan on this one was to do the area of the big circle minus the area of the small circle. And P is the center. It's got a diameter of 16, okay? So area of the big circle obviously would be pi r squared. If the diameter is 16, the r is going to be 6. And pi r squared, which is, you can see that this distance across right here is the diameter of the smaller circle, and the diameter of the small circle is the same as the radius of the big circle. So we can take half of the radius of the big circle, and that would be the radius of the small circle. So hopefully you plugged in, 6 squared is the radius of the big circle, and 3 squared as the radius of the small. So it's 36 pi minus 9 pi, which is 27 pi. Okay, we'll skip number 3 and go to number 4. So we have a regular hexagon of side 6. Give it a run for its money here. So the way I did this one was just said the area of the two triangles. Okay, I know it's a hexagon. My formula is going to be 2 times 1/2 base times height, so I need to figure out the base times height. I know that's 6, which means that's 6. This is actually fairly similar to one we just did earlier. So I know that in here, I'm going to end up getting a 30, 60, 90 triangle. Remember, interior angle of a hexagon is 120. If I drop an altitude in this isosceles triangle, it's going to be a perpendicular bisector. So I have a right angle. I know that this is going to be, this whole angle is bisected, so that's 60, and there's 30. So basically, again, my hypotenuse in this right triangle is 6, which means the side opposite is going to be 3. And then this opposite, the 60, is going to be 3 root 3. So the entire base is 3 root 3 plus 3 root 3, because there's 2 there, right? So 3 root 3 plus 3 root 3 is 6 root 3. That's my base. And my height we said was 3. And then we just do the math and get 18 pi. Awesome. Okay, number 5. So we have an equilateral triangle, TOY, so the big triangle there, really the only triangle there, I guess. Side length is 24, and we know MP and V are midpoints. All right, that's obviously important. So go ahead and give it a shot. Okay, well, hopefully you recognize that we basically have the triangle minus, if I do minus the area of 3 sections or parts of a circle, right? And, oops, there we go. So we have the area of the triangle minus the area of 3 1/6 circles. How do I know it's a sixth of a circle? Well, what's the measure of this angle right here? Right, it's an equilateral triangle, so it's 60. So 60 out of 360 is 1/6 of a circle. So our formulas that we're going to plug into, you got it, s squared root 3 over 4 minus 3 times the quantity 1/6 pi r squared. Okay, well, what's s? Well, that's easy. We know the side is 24, so we would plug that in. So that actually, 24 squared divided by 4 comes out to be 144 root 3. And r is what? Well, if these are midpoints, then we know the radius of that big circle there would be what? Half of 24, which is 12. And so we would plug in that. 12 squared, 144, and then divide that by 6, and multiply by 3 is going to get you 72. So we have 72 pi. Notice 144 times root 3 is going to be more than 72 times pi. Okay, we'll skip 6 and 7, and our last one will be number 8, which I think I can fit all in here. Good. Okay, so we have a square formed by joining midpoints of alternate sides, alternate meaning every other side, right, of a regular octagon. So we have a stop sign here with a square inside it, okay? And the regular octagon has sides of 10, okay? So these are all 10. This one is tough. Give it a shot. You can do it. Okay. So my game plan was the area of the 4 trapezoids, okay? And if I dropped altitudes here, right? Because I'm going to need to do that to find the area of the trapezoid. I would end up having 45, 45, 90 triangles. Okay? Why is that? Well, what do we know? We know that we have an angle here, right? And we have, if we drop an altitude, we're going to have a 90-degree angle. And what's the interior angle of an octagon? Okay, I hope you said 135, right? So if it's 135 and I drop a right angle here, right, then this is 90 degrees as well, right? And if that's 90, then that's going to leave this is 45 and that is 45. Okay, so I know that this is what? If the whole side is 10, I know that this is 5. So that's represented right here, okay? So that's 5. And if it's 45, 45, 90, and the 5 is opposite the right angle, it's a hypotenuse, what do we need to do? We need to divide by root 2. So 5 divided by root 2, multiply top and bottom by root 2, becomes 5 root 2 over 2. Okay, so I now know that I have a trapezoid that has one base that's 10, and then another one, which is going to be made up of 3 parts. It's going to be made up of this, which is 10, and then this, right? And what are those distances right there and right there? Yeah, they are 5 root 2 over 2. So we have 1/2 times the height times base 1 plus base 2. We have 1/2 5 root 2 over 2, right? That's the height, right? That's our height right here, okay? And then we have one base 1, which was 10, and then the other one, which was 10 here, this part right here in the middle, plus 10 plus 5 root 2, okay? So the reason we have the plus the 5 root 2 obviously is we have 5 root 2 over 2 and another 5 root 2 over 2. Well, doesn't that make 10 root 2 over 2 if we're adding them together, which is 5 root 2. Okay, so now we just got to simplify all that. Obviously, 1/2 times 5 root 2 over 2, and then multiply times 4 gets us 5 root 2, right? Because the 1/2 makes us 5 root 2 over 4, and then the 4's cancel. Here we have 20 plus 5 root 2, and then we can distribute 5 root 2 times 20 is 100 root 2. 5 root 2 times 5 root 2 becomes 25 times 2, which is 50. So 100 root 2 plus 50. Okay, so that's great. You can stop that. Our next video lesson will be on 16.5, and then we'll come back and do the shaded regions after we've done that, the rest of the shading regions that are here. Hope you had fun with those. Good stuff, challenging, but hopefully you conquered it. Bye-bye.